No doubt, so we can start.
Okay. You can see my screen, right?
No, sir.
No, sir.
No, sir.
No, sir.
Now you can see.
Yes, sir.
Pattern is nothing but association rule for us. Which item sets come together, that is pattern, or which item sets influence others to be part of that item set. So now we understand what is pattern evaluation. Association rule algorithms can produce large number of rules. So we have seen that if a frequent item set is having 5 elements, then we can make partitions of that frequent item set, one partition left side, other partition right side. That makes an association rule with some support and confidence. So if you have five elements in an item set, how many you can form association rules?
2 power 5 minus 2.
Right. So how many subsets you can form? For that, at least having one element, right? So you will remove only the full set and the empty set. Then all other subsets will give one partition for that item set. So 2 power 5 minus 2, 2 power 5, the total minus 2. So 2 power n minus 2. So that's a use number. So association rule algorithms can produce large number of rules. Interestingness measures can be used to prune, rank the patterns. There is no meaning of giving it, see whether it has good support, good confidence, whether it is useful for the people to make further analysis or use that information. There is no use if you throw thousands of rules or millions of rules. So then we need to find out what will be the interesting rule for the user. So we need to prune those rules so that only we should get interestingness, which has a good rule to use further. So we need to prune them before generating itself, then we will also reduce the complexity. In the original formulation, support and confidence are the only measures used. Now we will see that what are the drawbacks with them. So computing interestingness measure. So here we take one association rule, like given X that implies Y, or XY. XY is the frequent item set here. Then we are trying to form a rule, association rule, like whenever you see X, you will also see Y in that item set. Then what is support, what is confidence? That is what we were looking earlier. Information needed to compute interestingness can be obtained from a contingency table. So whenever an association rule comes, we will form a contingency table. It is similar to your confusion matrix type of thing. So here you see the table. X is one item. Non-X means anything other than X. Then Y is another item. Y complement is other than Y. So we are interested in the combination of X, Y. So we are looking that now Y comes along with X how many times? Y comes without X how many times? If it is same, Y comes irrespective of whether X is there or X is not there in that item set with same probability, then there is no meaning of this association rule. X is not bringing any new information that if X is there, Y also will be there. Most of that information you are not getting. So to understand that, we are creating this table. So why we are taking complement means we are looking that, okay, if X is there, what is probability that Y also will be there along with X? If X is not there, what is probability that Y will be there in that item set? These two things are important for us now. So this F11 means in the whole transaction set item sets, XY, how many times XY appeared? that is nothing but support here, support of X and Y. How many item sets have X and Y common? Then X, Y complement. What does it mean? F10 means?
Which contains X and does not contain Y.
Y. So item sets which has X, which have X but not Y. That is F10. So 1 is attached to X. The first index is attached to X. 1 means that item is there. 0 means that item is not there. Similarly, what is this F01?
Without item set X and with item set Y.
Right. So F00 means?
Without both of them.
Okay. And how do you understand this? F1 plus means? Item sets containing
X.
X. We are not worried about whether Y is there, Y not there, right? So F0 plus means under that, F1 plus under that.
Which doesn't have X.
Doesn't have X. So similarly, F plus 1 and F plus 0. Okay. Use it to define various measures. Now, how good the rule, we will use these 4 parameters. What are these 4 parameters? F11, F10, F01, F00. This is related to one association rule. Remember, for each association rule, we should form a contingency table to find out how interesting the rule is. Then there are different measures. We will not study all of them. It's whoever is interested, they can go and Google it and find out all these measures. But some of the things which are more generally used by people, they are support, confidence, Gini, entropy, etc. But we will concentrate mostly on lift, how much of lift we are getting. We will define what is lift. Of course, here, for all measures, a clear formulas are given. If somebody is interested, they can compute all those measures from these 4 values. So what is the drawback of confidence? If we use the confidence, can we say that the rule is very much interesting for us? Now we'll see this example. There are some transactions are given, and tea and coffee are 2 items. Then the right side is the contingency table for tea copy item set, means tea implies coffee. Then what is the meaning of 15 here in the right table?
In 15 instances, if tea comes, coffee also will be there.
In 15 item sets, you found tea and coffee together. Okay. What is the meaning of 5?
Only tea. I mean, other than coffee.
Yeah.
It has tea, but
coffee, without coffee, how many item sets has tea? Okay. Then 75 is without tea, how many item sets have coffee? Then 5 is without tea, without coffee, how many item sets we have in that transactions? Then we have 100 here. 100 is taken. It is easy to understand in percentages, right? Now we will see what is confidence for this. Confidence of this association rule, coffee implies tea, is do you remember? How do you get the confidence of the association rule?
Support of the entire frequency by support of X.
Right. Combinedly coffee and tea divided by only tea, right? Whatever is there later in this after the numerator denominator. So T support. What is the T support here from the contingency table?
20.
That is nothing but how many item sets have T?
Right.
20, right?
Yes.
15 with coffee, without coffee, 5. So 20 item sets have T means support of T is 20. That's why it is coming in the denominator. What is this 15?
Both coffee.
only both coffee.
Support of the both coffee and tea together. So you got 0.75. Means 75% times or 75% times you see – whenever people purchase tea, they will also purchase coffee. 75% times you see, whenever people purchase tea, they will also purchase coffee. 75% times you see, whenever people purchase tea, they will also purchase coffee. 75% times you see, whenever people purchase tea, they will also purchase coffee. 75% times you see, whenever people purchase tea, they will also purchase coffee. 75% times you see, whenever people purchase tea, they will also purchase coffee. 75% times you see, whenever people purchase tea, they will also purchase coffee. 75% times you see, whenever people purchase tea, they will also purchase coffee. 75% times you see, whenever people purchase tea, they will also purchase coffee. 75% times you see, whenever people purchase tea, they will also purchase coffee. 75% times you see, whenever people purchase tea, they will also purchase coffee. 75% times you see, whenever people purchase tea, they will also purchase coffee. 75% times you see, whenever people purchase tea So what do you think? Is this rule looks good for us?
With respect to confidence, it looks good because it's more than 50%.
But if somebody says that it's 75% times people purchase together coffee and tea, it looks good, right? For general sense.
Right.
So confidence greater than 50%, meaning people who drink tea are more likely to drink coffee than not drink coffee. So rule seems reasonable. Okay, now we will find out what is the confidence of not coffee or probability of not coffee in the total transactions or in total item sets. Total transaction, that is nothing but. There are 100, right? What is the not coffee here you find here?
10.
10.
Mm.
So not coffee is
90, sir. 100 minus 10.
100 minus 10, right? What is this number? Not coffee, 10. Coffee 90. Okay, coffee is 90, so not coffee is 10. 10 by 100 is the, why we are getting 0.9?
Sir, to overall persons who are drinking coffee is 90%. You can, but without coffee it is only 10% also.
Okay, so he is giving in fractions then, not percentages. So 0.9. Anyway, even above also we got 0.75, right? So it is not percentages, it is in fractions. So 0.9 fraction of people will not drink coffee. Which means knowing that a person drinks tea reduces the probability that the person drinks coffee. I think this is a mistake. Okay.
I think it should be 0.1, sir.
Yeah. No. The whatever we are doing, the analysis. Let's say when we make these things, these come separately. This shouldn't be there. Now it looks good. Okay. Now coffee is 0.9 because 90 by 100 is 0.9, right? How many people drink coffee? So in the total transactions, it is 0.9. But when they take tea, what is probability that they also take coffee?
0.75.
Which one is more?
Probability of only coffee.
So if they don't take tea, then only there is more probability, right? They take coffee here.
Right.
If they take tea, then the probability is becoming less, 0.75, coming down. So now we can understand that whatever the rule earlier, based on confidence, it looks like it was a good rule. But after looking this in the entire data set, so 0.90% of the people, they drink coffee. So means 90% of the times they drink coffee. But if they take tea, that is coming down to 75%. Now, do we say this rule is interesting for us?
Purchase of coffee is not even dependent on tea. I mean, it is purchased more than it is purchased individually.
It is reducing actually.
Right.
So don't look at with the tea, right? And note that probability of not coffee given tea. So what is that? Given support of tea is anyway 80. What is not coffee and tea support? 75, right? Not coffee and tea. Again, this also shouldn't be there, I think. Coffee and tea. This is not tea. Okay. Okay. Now, what is the support of not tea? Right? Not T support is how much here?
80.
80. So that will come in the denominator. What is the support of coffee and not tea?
25.
75. 75 by 8. Means this rule is more interesting. If they don't take tea, then they take more coffee, right?
Right.
So the people take coffee. If they don't take, if they take tea, then it is coming down to 0.75. If they don't take tea, then it is increasing more than the 0.9, that is 0.9375. So which rule is interesting to tell to the people? The coffee implies tea or coffee implies doesn't tea?
I think it's reverse, no, sir. Tea implies coffee or without tea implies coffee.
That also okay, but according to this, it's saying not taking tea. We don't have item set like that. It's not taking tea. You are right. But only to compare this, I'm just saying that it's if they take tea, then it is coming down. If they don't take tea, it is going up.
Right.
So this confidence is not a good measure for us because we have seen an example now that it's saying, though it is not such interesting thing, we are getting as if it's a good rule earlier. Once we verified it, see clearly the coffee support and the probability of people taking coffee in the entire population, actually tea is bringing down, it's saying. So that's why the rule is not interesting. So that is one drawback which we will go through if we go by only confidence, and that is the drawback which we found. So what measures we need to have then? So what kind of rules do we really want? Confidence X to Y should be sufficiently high. Means more times you should be able to observe that happened in the data set. If you observe once, twice, thrice, then that doesn't mean. That's why confidence should be high. To ensure that people who buy X will more likely buy Y than not buy Y. This also is important. So whether X ensures buying Y more or not buying Y more. Because we have seen earlier the confidence not buying coffee is more there instead of buying coffee. So that also to be verified. So confidence X to Y greater than support of Y. Another, see the support of Y. Okay, this confidence should be greater than support of Y. Otherwise, rule will be misleading because having item X actually reduces the chance of having item Y in the same transaction. So we also need to have confidence should be always greater than the support of Y. So this confidence here we have seen if this 0.75 is less than 0.9, right? That is what we are getting problem now.
Right.
So that's why we also need confidence of X to Y greater than support of Y. So these two things we need to consider now. One is the confidence should be high, the first thing, because it should be more frequent to state that observation is valid. Then the second thing is the confidence of X to Y should be greater than support of Y. Otherwise, rule will be misleading because having item X actually reduces the chance of having item Y in the same transaction. That is what we observed just now. Is there any measure that captures this constraint? So now we need to check, do we define a measure or do we get a measure to capture this constraint? Confidence X to Y greater than support Y. Answer, yes, there are many of them. Not one, many of them are there. The first thing is the statistical independence. The criterion confidence X to Y equal to support of Y is equivalent to what is confidence of X to Y? Support of X and Y by support of Y, right? Support of X and Y, if that is equal to Px and Py. Say in statistics probability independent, if Y is independent of X, then you can simply multiply those probabilities. That is what here happening. So Py given X equal to Py means it is independent of X. This X is not changing probability of observing Y, whether X is there or not X is there. Then we say Py given X equal to Py. There is also definition for independent observations. in probability if Py given X equal to Py. In definition, it is actually Py intersection X by Px. Then in other definition is Pxy equal to Px and multiplied by Py. If Pxy greater than Pxpy, so you need to get the probability of X in the data set, probability of Y in the data set, just multiply and see that how many items, probability of they are coming together, that is the Pxy. If that is greater than, X and Y are positively correlated. So most of the times you see more than, the probability is more than their multiplication of individual probabilities. If Pxy less than Pxpy, X and Y are negatively correlated. Means you see less number of times than the Px into Py. So measures that take into account statistical dependence is lift and interest. Both are same. They are not different. Lift is used for rules while interest is used for item sets. But formula is same. Py given X, according to the probability formula, this is P, Y and X together divided by Px. The first one I am talking about, Py given X, is nothing but see this first part is equal to P comma X Y divided by Px. And still you have 1 by Py, right? So that's why this Py also will come here. So according to the probability formulas, this is exactly whatever you are writing down. But when we say for a association rule, we call this value lift. When we talk about the item sets, we say interest. These two formulas are same, lift and interest. When we talk about the rules, we say how much of lift this association rule has. When we talk about the item sets, how much of interest this item set. That is what we say. Is it clear what I'm saying?
Yes.
Lift and interest formula is same, but the terminology we will use, lift for association rule, interest for the item set.
But for the item set, there is no differentiation as X and Y, right? That will only come when we create rules.
I don't know, item set, there are two items, right? X and Y.
Okay,
Just to look at the item set itself, how much it is interesting.
Okay.
We are not forming any rule there. So how frequent they come together, let's say. Are they coming together, let's say, more than individual probability multiplication or less than individual probability multiplication? That's all, let's say, item sets. So if somebody want to explain only in terms of the item set, not using any association rule or anything, then they will say that interest, because there is nothing like lift there. So lift Y we use means we are saying that it's the probability of Y is lifted when you have X in that item set. That's why the lift, the terminology has value there. Right. When you have a rule, you are saying that it's the probability of Y is lifted by X. Means what? Whenever X is there, then probability of Y is more to be in that item set. You understand why this lift has come, the terminology?
Yes.
Interest is just, let's say, whether this item set is interest or not. We are not talking about any rule or any lifting or anything there. How interest this item set being together X and Y, something like that. These may be two sets also. X is one set, Y is another set. Then let's say what is the probability of that first item set, then second item set multiplications. Coming both item sets together, like that also you can see. Lift is used for rules while interest is used for item sets. Then another word, PS. I don't know exactly what is the expansion of this PS. Can anybody check Google and find out? Probability of XY minus probability of X, probability of Y. So the difference actually this is. There may be some expansion for this PS. I don't know right now. We'll see that later. So this is it's the difference between probability of XY together and minus or probability of multiplications of individual probabilities of them. Then another is phi minus coefficient, that is Pxy minus Pxpy, that is nothing but Ps, under root of Px 1 minus Px, Py 1 minus Py. This is something like a standard deviation. If anybody knows the probabilities, then 1 minus P is the probability of not, right? Yes, probability is P, then 1 minus P is the not. If it is a binomial, we are considering only binomial here because X and not X type. Then Y and not Y. So this is correlation coefficient, something we can say that it's if we understand the statistics. So phi minus coefficient or phi coefficient, not minus, phi coefficient is Pxy minus Pxpy under root of Px 1 minus Px. This is standard deviation of X. Py 1 minus Py is the standard deviation of the root of Py 1 minus Py is the standard deviations of the binomial of Y. In binomial distribution, the standard deviation is P into 1 minus P under root. But anyway, we need to understand simple thing here. This lift is Py given X by Py or Pxy divided by Pxpy. So now we will find out lift. Will it make our rules interesting to find out whether it is interesting or not and make sense or not? The same table we are taking. Now confidence, this anyway we found out earlier 0.75. We also find out, this is wrong again. This is P of coffee is 0.9. We will remove this. Then lift equal to 0.75 by 0.9. What is the formula for lift?
P of X and Y by P of Y.
Yeah. This confidence of coffee and tea, right? Coffee given tea, right? This is 0.75. So P coffee given tea by P of T. So P of, okay, here it is. We are more interested to see coffee. So P of Y, right? This rule, let's say, when we write T implies coffee, but when we write probability of coffee given T, so that's why T is coming later.
Right.
That we should understand it. See the difference. P y given X means the rule becomes X to Y. But when we compute the probabilities, we write P y given X. Y, this bar is called a given. So when X is present, then what is probability of Y? That is what the meaning P y given X. So here also, the rule is T implies coffee. Then we want probability of coffee, that is 0.9. Lift is nothing but the rule confidence T2 coffee, that is nothing but probability of coffee given T, that is 0.75. Then probability of coffee is 0.9. So you take this 0.8333 less than 1 means therefore is negatively associated. What is the meaning of negatively associated?
With the increase of probability of T, coffee decreases.
Decreases. So is it enough to use confidence lift for pruning? That is one more question we have. We need to verify in later slides. So is it enough just to go by confidence and lift for pruning? But anyway, in pruning, this will go out, right? This is not interesting thing. There is no lift for coffee. So lift or interest, whatever that you find out here. So xy, what is probability of x and y together?
10,
10 by 100.
100.
That is
0.1.
0.1. What is probability of x?
0.1.
What is probability of y? Y is also
0.1.
0.1. So lift is nothing but 0.1 by 0.1, 0.1. That is 10 for this table.
Right.
So now we have bigger numbers. All the time, whenever they purchased coffee, they also purchased tea. This is nothing but 90. And x is 90, y is also 90, right?
Right.
So here also, 10 times they purchased y, then 10 times they purchased x. Both also purchased 10 times, means all the time they are purchasing together. Then what is happening in lift? For first one, lift is 10. For second one, lift is 1 minus 1.11. So statistical independence. So this lift is also sometimes misleading, because it is 100% sure that whenever they take tea, they're also taking coffee, right? Here in this both tables.
Right.
But one is increasing the lift to 10, other one is not increasing in the same way. It is increasing still, but not in the same way. So if pxy equal to pxpy, that implies lift equal to 1. If it is independent, then lift will become 1. So lift is also sometimes may not be that accurate measure to find out interestingness, because both are interesting, because we have seen in both cases, whenever the only thing is for first case, the confidence is less. For second case, confidence is more. Am I right? 90 times you observed they are purchasing together, right? In second table.
Right.
First table, they only observed 10 times. So people may say, okay, 10 times they might have become random. What guarantee that it's remaining 90 times? Here, there is no such question. It's out of 100 times, 90 times you observed. They purchase it together. Then there is no question of what happens in 10. Even if 10 goes wrong, then your percentage won't come down. So that's why the second one is giving more confidence, is giving lift is also dependent on confidence. So it is also giving more confidence, the second one. But lift is coming less here. So that's why there are many measures in the literature to find out interestingness. A list is given here. Phi coefficient, we have seen just now, it's earlier also. Then Goodman, Kruskal's lambda, odds ratio, PAB, P A naught B naught divided by PAB, P A B naught, P A naught B, something like that, it's see. Yule's Q, Yule's Y, kappa, mutual information, J measure, this is Jaccard measure, Gini index, support, simply support also you can take, confidence. If you take support, then in the earlier example, this second one will be more good rule than the first one, because that has more support. Laplace, conviction, interest we have seen already. Interest and lift is same. That's why you don't see lift again. Then cosine, Piotr-Shapiro's, PS means this. We have seen just now, right? PS. I told you that I don't know what is this PS, but here the expansion is there. Piotr-Shapiro's, maybe some Russian scientist. Certainty factor, added value. Added value is the difference. Then collective strength, again another Jaccard. Then close scan. So all these measures are there. It's we are not going to discuss each of these measures. If any problem you want to see that it's, if you want to apply different measures and see that it's to separate or prune association rules, you can take all these things. Most of these things may come with a package. In that package, you need to select which measure you want. Then again, empirically or experimentally, you need to see that it's how good rules you're getting, whether they are interesting for the customer or not. Based on customer, you will select one of these things. So comparing different measures, this simply they have given 10 examples with they have already computed these contingency values F11, F10, F01, F00. Then when you compute by using those formulas, then what values you will get here? For E1, pi value is 1, lambda value is 1. So for us, lift, right? Lift is 5 years. L means, I think, lift, or I is interestingness. Okay. L may be Laplacian. So I is 6. So if you are interested to see only this I, for which example you have highest I year interestingness?
Third one.
Third one. See what is E3 there. So 9481 means high support it has, right? Highest support in the whole data set it has for coming together. Then F1094. Not having the second item is 94, only having first item. But not having first item, having second item is 127. Then F009 Anyway, it looks like that. It's this confidence is very, very high for this. And non-items are also very less, not coming. So that's why it won't reduce. In the total also, F1 is coming, F01 is coming 127, and where is another one? 127 plus 9481 Y's are there. That is what you need to understand. So you can compute all these things. So most of the times they are showing that here, the measures will differ in a views way. So that's why you need to see what is the customer is looking. Based on that, you need to select these measures. What do you find out, or what do you make by looking at these two circled things?
One measure is giving low value and one measure is giving high value.
High value. In the same, if you see your Gini index, this is G, E10 is getting highest value. In another measure, this is getting lowest value. So that's why you need to see what is customer interest. What is he looking? Because is he looking that it's a negatively correlation or positively correlation? Those things you need to see that first, understand. Based on that, select one of these measures, because these measures change drastically from one measure to other measure. These are not compatible. If it is great in one measure, it may not be that great in another measure. So property under variable permutation. These are nothing but if you change the data sets, then how do they change? So does MAB is equal to measure, AB is equal to measure of BA. If it is equal, then it is called symmetric measure. What is the difference between measure of AB and measure of BA? For this in denominator, what support will come?
B.
For the second one?
A.
So they are different, let's say, for some of the things. If you go by lift, lift is also not different. That is what here we are getting. Support, lift. Support is nothing but anyway getting together AB, that is same. And lift is also not changes. That is what here said, MAB. Because in lift, you got MB and MA both, right? PA and PB both in the denominator, if you remember.
Right.
PXPY. So lift also, whether you take A first, B second, or B first, A second, you will get the same symmetry. Then collective strength, cosine. Anyway, we haven't gone through these formulas. So these two we know. Support is nothing but whether A and B coming together, B and A coming together, it is same. Lift also, it is divided by individual probabilities of A and B, of combined probability of A and B. That's why these two are symmetric measures. Asymmetric measures, confidence. Confidence only one will come in the denominator. Am I right?
Yes.
And for this, B will come in the denominator, probability B. This probability A will come here, right? So that's why they differ. So anyway, we haven't gone through those measures. You can go through those measures. Property under row column scaling. So here female 2, 1, that is multiplied with 2. Male column is multiplied with 10. Then do they change? Underlying association should be independent of the relative number of male and female students in the samples. Then it is called Mosteller. Then another way, this is just if you multiply, what will happen? See that will it change or not? You need to find out lift, and that is an exercise for you. Interestingness and confidence. You see that it's how do they change when you multiply with some constants, will exactly increase 2 times or 10 times, whatever that it's. Property under inversion operation. So if you change a complement instead of A, instead of B complement, then how do these measures will change? If you see A, then if you see C is completely, wherever ones are there, they converted into zeros, zeros converted into ones of A, right? Look at
Yes.
it, right? So this is inversion, means they are inverting the values 1 to 0, 0 to 1. And B also, they did the same thing.
Yes.
Then find out what will happen now. What is the lift year and what is the lift year? Okay. If that doesn't change, then it is invariant of inversion operation. Whether you invert or you will get the same lift. That is what we will say. So you need to find out it. See, it is an exercise for you. Find out lift for AB, find out lift for CD. That is nothing but inversion. Only if you invert only one column, then what will happen? That is nothing but E and F. Then again, you need to find out lift for E and F and see that A is inverted like E here, wherever ones are there, zeros are there ones. Then B is as it is. Then what will happen? So all these things are to be experimented or are to be computed as an examples. Okay, another example is the phi coefficient. Phi coefficient is analogous to correlation coefficient for continuous variables. Correlation coefficient is the statistical relationship between two variables. So if you find correlation coefficient, the formulas are given here. Remember it. So if you want, go and see here the formula, then use that formula. Then you will get correlation coefficient is 0.5238 for first one, 0.5238 for the second one. What is the difference between first one and second one? Values are same, but they are altered here. Right? 60, 20, 10, 10. Those values are same, right? In both tables.
X and Y are inverted.
So coefficient will not change. Correlation coefficient will not change whenever you invert them. Property under null addition, if you add values for some, what will happen? Then again, invariant measures, support won't change. Then cosine measure, Jacob measure also will not change, but correlation, Gini, mutual information, odds ratio, these will change whenever you add some values to the existing values. So here, what will change, what measures will not change under different transformations are given as a summary. Phi coefficient, correlation coefficient, under inversion, it is invariant. Yes means not change. Invariant means not change. Invariant S means not change, remember. So null addition, if you add some values, then correlation coefficient will change. Scaling also not invariant. So like that you will see. What about this interest? Interest under inversion, what will happen? It changes its values. So interest is not invariant for any of these transformations. Is there anything which will be invariant for all these transformations? No, right? There is no S for all three columns. There's another thing, it's a Simpson's paradox. Usually it's in mathematics. Russell's paradox is there in set theory. Like that, Simpson's paradox is also one, it's a, which will confuse the people. There is no definite answer for that. It's in Russell's paradox. What is the example is, the set contains all the people who doesn't, who will shave, who will get shaved by a barber. Then second set will consist all the people who shave themselves. Then barber belongs to which set? He belongs to both sets, right? So if you want to make two distinct subsets, you cannot make that. That is always a problem there, because he saves himself, or because he himself is a barber, he is also getting shaved by a barber. Both are true in that case. So if you cannot put it, say, if you want to ask to choose one, you cannot choose that. You need to put that aside, an exceptional case. So like that, Simpson's paradox will see that what's happening here. Buy HD TV, buy exercise machine. So then yes and no. Yes means 1, no means 0. You can think like that. So F11 is 99, F10 is 81, like that. So confidence of HD TV equal to yes implies exercise machine, yes, is 55%. Confidence of HD TV no, exercise machine yes equal to 45%. Customers who buy HD TV are more likely to buy exercise machines because of these two rules, right? The first one says that HD, whenever they purchase HD TV, they also purchase exercise machine. But is there really a relation between HD TV and exercise machine? That is what, or some other thing is influencing this. This is called causal relation. There are two examples they give. One example is, let's say, if they don't understand correctly the relationship. In some study, they found most of the seashells are killed when more ice creams are consumed at beaches. Then they thought that it's if you buy more ice creams, then more seashells will die, something like that. But actual relation is when people buy more ice creams, when there is more hotness actually bringing this, seashells are, because of that, whatever that the sea animals, they are died because of the heat. The relationship is not between ice creams and the death of those sea animals. So if we don't understand the third thing, because of the heat, people purchase more, because of the heat, they are dying. So it is not, to reduce the number of deaths of sea animals, purchase more ice creams. But if you say that more ice creams, whenever people purchase more ice creams, then more deaths means they need to stop ice creams. It is not the exact relationship which we grasped correctly. The grasping correctly is heat is the thing. Like that here, whether it is simply buying HDTV is making exercise machine, or is there any other thing actually making this relation, this to buy more exercise machines. So that is what we need to find out. Okay, now college students we are looking. In the subcategory we are taking in that. So in college students, HDTV, whenever they purchase HDTV, they also purchase exercise machine, 10%. When they purchase no HDTV, then they purchase exercise machine is 11.8%, a marginal increase here. In working adults, whenever they purchase HDTV, they are also purchasing exercise machine with 57%. Whenever they are purchasing, not purchasing HDTV, still they are purchasing exercise machine is 58.1%. So if you look at these underlining populations, they are almost same, right? They are not much difference. 10 and 11, 57 and 58. Observed relationship in data may be influenced by the presence of other confounding factors, hidden variables. Maybe because of this, see, more and more college students are present in the survey. That's where the difference, almost here, how much of difference is there? 20% difference is there. 1.8 means more than 10.
Yeah.
So 100, it is 18, right?
Yes.
And here, how much of difference is there? This is very less difference is there. This is not even 2%, right? The difference is for working adults.
Yes.
2 to 20%. So in the survey, there are more college students because of the college students, exercise machine is purchased more. If your survey, you have more college students, not because of it, see, they are purchasing HTTV, they are also purchasing. This is a misleading information actually. There is no causal relationship, but we are trying to find out a causal relationship. The causal relationship may be this college students means they are more prone to do more exercise. That's why they purchase exercise machines. They're also more spent to in entertainment. So they go for this HDTV. So that is what we need to understand. So observed relationship in data may be influenced by the presence of other confounding factors. Hidden variables may cause the observed relationship to disappear or reverse its direction. So we need to reverse and see that that's why whether it is invariant or not. All those measures we are trying to see that, make it inverse and see whether still you get same or not. So proper satisfaction is needed to avoid generating spurious patterns. In some medical study also, these examples are important. When we say these association rules, these things. In medical study also, they found in simple association rule, whenever people go for cosmetics consumption more, then they are less prone to get cancer. That is what this causal, this association rule, when they mined, they got that. But later on, they found that not because of the cosmetics consumption. This is because of the rich people. So more rich, then less prone to cancer. That is what they found, because more rich means more nutritious food, all those things, not only just cosmetics, other even medicines, in time taking, all those things. What they did, they separated the population. Rich population, in that more consumption, how is it affecting the cancer? In not rich population, then they found very less number of people will take cosmetics. But anyway, they also separated that, they studied. When they studied, they found that cosmetics who are rich and they are more consuming the cosmetics, then they are more prone to get the cancer. When you combine the population, very few people will be there, right? Rich people. That is the problem. Then they don't actually change all these things because of the poverty or less, not rich. That's why they are unable to afford the thing. The cancer is prevalent in all the sections, but when you want to see that whether richness leads to cancer or richness and using the consumption of the cosmetics leads to cancer, that they found when they were able to separate the populations. When they took the population together, then they got a misleading rule there. Then people thought that who take more cosmetics, then they will get less prone to cancer, which is not a correct rule or correct association. So those things will come. That's why we need to be careful. That's why the Simpson paradox, this is given. So don't go by just on the whole population. You may also need to reverse the rules and see what will happen. So that's why it said proper satisfaction is needed to avoid generating spurious patterns. This is, these are not manually, these are to be done manually to understand what's happening, whether we are getting good rules or not. Is this association rule is meaningful or not? If it is not meaningful, then how do we see that it is misleading? These are not something like your packages, machine learning packages or other pre-processing packages which we have seen. These things, as many examples you see, then you get experience, then you find then how to avoid these misleading results. This is one of the important thing in data science. So effect of support distribution and association mining. Many real data sets have skewed support distribution. Skewed means it's for item sets, more support, for some item sets, very less support. So support distribution of a retail data set, usually it's a less number of items. Rank of item in log scale and support count. So if you take it, see, there are more and more will have support count 1 is less. Similarly, it's support count with 10 power 1 rank of items means highest ranked item will have less support. Rank of item in log scale they are giving. This you need to understand. The y-axis is the support count. So more support count, then your rank will become less. 10 power 0 is 1, right? 10 power 1 is 10. So if your rank is 10, then you are getting less support. So highly ranked items are getting less support. So what is rank? We need to understand. Then rank may be interestingness. Some interestingness, they are looking whether it has good support or not. So highly ranked things will have less support. So few items with high support, many items with low support. So where do you want to find out rules according to the first principle? In the where you have more support, right?
Yes.
So your rules should come between 0 to this 10 power 1 or 1 to 10 power 1, these things. So few items with high support, wherever high support is there, then you'll get more confidence. That's why your rules should be based on these limited number of item sets, not with the very small supports. As you go forward, then with little support, there are many items are there. So those will not anyway give you any interesting rules. Difficult to set the appropriate min support threshold. If min support is too high, we could miss item sets involving interesting rare items. Example, caviar, vodka. Some example is given from some transaction data set. If min support is too low, it is computationally expensive and the number of item sets is very large. So what does it mean? So you should be careful when you are deciding the minimum support. If minimum support is too high, what will happen?
Less number of frequent items.
Less number of rules. Then you may miss many of the interesting rules also.
Right.
If you increase the minimum support, what will happen?
More number of rules and more number of complex.
More number of rules. And again, you need to compute whether they are interesting or not, right? More computation. First, to find out the rules itself is more computing. Later on, to find out whether they are interesting or not, another computational complexity will be added. So you should take carefully that it's depending on the problem, then how good rules you want, how much of computation power you have. Based on that, you need to select this minimum support. Then cross support patterns. A cross support pattern involves items with varying degree of support. Means one item is having very less support, other item is having very large support. So here caviar and milk. So if you want to find out the relationship between caviar and milk, milk is having huge support and caviar is having less support. Then how to avoid such patterns? This actually, it's irrespective of caviar. People may purchase milk like earlier, right? Irrespective of tea, people may purchase coffee.
Right.
So if you see that whoever purchase milk, they may also, the caviar people also need milk, but milk people, people who are purchasing milk, they may not need this caviar. So it misleads if you just say that 500, it's whenever they are purchasing, they are also purchasing milk. So how to avoid such patterns? 100% sometimes you may get, but that is misleading. Not milk is also 100% or more than that sometimes. So a measure of cross support, given an item set X with D items, we can define a measure of cross support R for the item set Rx equal to minimum of Sx1, Sx2, Sxt by maximum of Sx1, Sx2, Sxt. This is nothing but ratio of the minimums. Whatever minimum, it's whichever item has minimum support, that you take numerator, whatever item has maximum support, you take that as the denominator, then you get the ratio, where Sxi is the support of item Xi. Can use Rx to prune cross support patterns, but not to avoid them. So you can prune based on this. Let's see, if this ratio is very, very small, then don't consider them. Because they are very rare items, they actually don't influence the very frequent items, in fact. So that is what the underlying thing here. Confidence and cross support patterns, observation here, caviar and milk is very high. Confidence of caviar milk, as I told you, it's everybody want milk, whether they take caviar or not. Even if they take caviar, then they purchase milk. So that's why the confidence is very high. But confidence of milk to caviar is very low, because large number of people purchase milk, but they don't purchase caviar. That's why it is very low. Therefore, minimum of what will happen? Minimum, this the second one will come very small number, and the maximum, the first one, yeah, second one will come in numerator. First one will go in the denominator. So that's why it also becomes low. Your R value will become low. Then we don't find such rules based on it. Say one is having very small, other one is having very high. We are not giving some, we are using this ratio R. Then another measure is H confidence. To avoid patterns whose items have very different support, define a new evaluation measure for item sets known as H confidence or all confidence. Specifically given item set X with D items, H confidence is the minimum confidence of any association rule formed from item set X. So you form all rules, then get the minimum confidence rule. H confidence X equal to minimum of confidence X1 to X2. What is X1 and what is X2 in this? So you do partition of that item set. For whichever partition, for each partition you'll get a rule. For whichever partition you get less confidence or minimum confidence, that only you need to consider as the H confidence of X, where X1, X2 in X, X1 intersection X2 is phi, X1 union X2 equal to X. That is nothing but partition description they are giving here. For example, X1 equal to X1, X2, X2 will become X3, XD. All other items which are not part of this first part, X1, X2. There are D items, right? Then X3 to X2 will have second one. But given an item set X, what is the lowest confidence rule you can obtain from X? Recall is giving further analysis. When will we get lowest confidence? So recall from confidence X1 to X2. This is partition of X, right? Always.
Right.
So in the above, always you will get S support of X1 union X2. Always that item set frequency. Only denominator will change, support of X1. So only first set will change the confidence of the rule. So the numerator is fixed. Thus, to find the lowest confidence rule, we need to find the X1 with highest support. So which one is having highest support, you need to find out. Consider only rules where X is a single item. That is X1, X minus X1, X minus X1. This is a partition of X. X1 is one side, remaining all elements other side. Similarly like that, H confidence of X equal to minimum of this Sx by Sx1, Sx by Sx2, Sx by Sxt. Then this is Sx by maximum of Sx1, Sx2, Sxt. So your confidence of H confidence of X is dependent on the item which has maximum support in that item set. So by the anti-monotone property of support, means whenever you increase the item set, your support will reduce. That is what we discussed in earlier sessions also. So that is called anti-monotone property. If item set is reduced, support also will increase. So Sx less than or equal to a minimum of Sx1, Sx2, Sxt. Therefore, we can derive a relationship between the H confidence and cross support of an item set. So H confidence X is Sx by maximum of this. This is always less than or equal to a minimum of Sx1, Sx2, Sxt, maximum of Sx1. Because this Sx1, Sx2, Sxt, this is the anti-monotone property. Anything if you take more, then this only will get maximum here. For those sets, you will get still less support. So that's why this H confidence X is always less than or equal to Rx. This is the Rx formula, whatever we have written here. There's H confidence of X less than or equal to Rx. So since H confidence X less than or equal to Rx, we can eliminate cross support patterns by finding patterns with H confidence less than Hc, a user set threshold. Notice that 0 less than or equal to H confidence X less than or equal to Rx less than or equal to 1. Then to reduce the R prone, you can use H confidence, you put a threshold between 0 and 1. This particular thing is saying that you set your threshold between 0 and 1 because the value of H confidence X is always between 0 and 1. Any item set satisfying a given H confidence threshold, HC is called a hyperclick. Any item set satisfying a given H confidence threshold, this HC user input is called hyperclick. H confidence can be used instead of or in conjunction with support. That is up to the user. They can first put a support threshold, then H confidence threshold. That is also okay, or without support threshold also. Hyperclicks are item sets, but not necessarily frequent item sets. Good for finding low support patterns. So if you put support threshold, then you are also insisting that should have more support. But hyperclicks will also bring out less support patterns also. If they are interesting, we need to verify them. H confidence is anti-monotone again. H confidence like support, anti-monotone. Can define closed and maximal hyperclicks in terms of H confidence. Yeah, hyperclick X is closed if none of its immediate supersets has the same H confidence as X. We have studied closed sets, open sets. The same analogy here it is used. A hyperclick X is maximal if H confidence X less than or equal to Hc and none of its immediate supersets Y have H confidence Y less than or equal to Hc. So hyperclicks have the high affinity property. Think of the individual items as sparse binary vectors. H confidence gives us information about their pairwise Jacob and cosine similarity. These are another measures which we have seen in that list. Assume X1 and X2 are only two items in an item set X. Jacob X1, X2 greater than or equal to H confidence of X by 2. Cosine X1, X2 is also greater than H confidence of X. Hyperclicks that have a high H confidence consist of very similar items as measured by Jacob and cosine. The items in a hyperclick cannot have widely different support. Allows for more efficient pruning. So if they have widely different support, then your H-click value will become less. So they don't cross the threshold. That's why you'll get less rules. That is one type of pruning. So one example of applications of hyperclicks is hyperclicks are used to find strongly coherent groups of items. Words that occur together in documents. So where people use these hyperclicks, this is one application. Words that occur together in documents, proteins in a protein interaction network. So here one example is given in the figure at the right. A gene ontology hierarchy for biological process shows that the identified proteins in the hyperclick PRE to SCL1 perform the same function and involved in the same biological process. So they used this hyperclick for some biological process. And they found out that exactly they perform the same process in both. So biological process, then physiological process, then metabolism, then catabolism, all these things are in the same. So they are less than some p-value here. All these are coming here the same, right? PRE2, PRE4. So actually we need to take the full example and see, you can actually search for this example, how they are using hyperclicks to find out proteins in a protein interaction network, or look out some example, let's say online, if somebody provides, how they are using hyperclicks to find out words that occur together in documents. Why do you need words occur in together in documents? Any idea? I don't know much about the biological process, but we do this data science. Most of the times we see that which words come together for many examples. You have any idea where it is important?
Topic modeling.
Yeah, in topic modeling is one, in many, right? Even chatbots also,
Right.
because the words together will change the meaning of that phrase. If you consider individually, it is different. Meaning will come. So when you are finding frequencies of words, don't look at their frequency. See, most of the times we will try to see that the two documents, whether they are same or not, based on frequency of words. So if you take individually, then most of the words will have the same frequency. But if you consider these words occur together, they are also called bigrams. Bigrams, meaningful bigrams again. So when they are together, their meaning will be changed. When they are not together, then their meaning is something different. So we need to separate them to consider them as a single word. So there we require these words that occur together. So many NLP basic techniques, they work with words, and they work with the semantics, not only syntactic meaning, semantic. Whenever you want semantic meaning, then word order is also important, and word occurring together is also important. So that is the difficult thing, where they are still finding different methods to find out. So one of the methods to find out how often they occur together is application of the hyperclicks. So you can search that, how do they use hyperclicks to find out words that occur together in documents. Then see that example. Then you learn more, how this association analysis applications are into different domains. Most of the times, whatever text you take, they start with the market basket analysis, some transactions that So if you want to learn more, then you need to see such things. So it is 12:17. I'll stop it here. Any questions, then I'll take now. Otherwise, you can go through again these slides and textbook. We can discuss tomorrow if you have still doubts. I'll also stop this recording.